Okay, so as always, when we talk about spectroscopy, we're going to start off with IR. And like we talked about with IR for carboxylic acid, not for carboxylic acids, for other carbonyls, IR for carboxylic acid derivatives is not so helpful because they all contain carbonyl groups, yay, and then that's about it. Lots of things contain carbonyl groups. There is a table I've put up here that'll show you anywhere from 1700 to 1800. Look at all the different types of groups that can be on there. These are posted on Blackboard too, if you want. So if you see a carbonyl in there, that's helpful. You know, it's a carbonyl, but beyond that, you're going to have to use your imagination when you get to the NMR. So let's talk about NMR. No, okay, that's another IR. See, carbonyl present. All this tells you is that a carbon-oxygen double bond is in there. There is no carboxylic acid over here, so that's great. But otherwise, we don't have a lot of information to go on. So here is an example of a ester. What's the name of this ester? Ethyl ethanoate, or if you want to sound like a cool kid, use the common name ethyl acetate. This is the ethyl group attached onto the ester. That is an ethanoic acid or ethanoate, so that is the proper name for it. This would have a formula of C 4 H 3 4 5 6 7 8 O2. How many degrees of sorry, what's our fake formula we're going to use here? C4H8. Right, so we're going to just ignore both those oxygens. A saturated molecule with 4 carbons would have how many hydrogens? 10. You might notice we are missing 2 hydrogens from there, which tells us we have 1 degree of unsaturation. Most of you have picked up on this, but some of you still do not show me your degrees of unsaturation when you solve NMR. If you are in that camp, stop it. Start doing that. Show me the degrees of unsaturation. Stop not showing me the degrees of saturation. This will help you. It'll get you points and it will help you, I promise. This degree of unsaturation tells us we either have a ring or more likely a double bond, right? And since we have 2 oxygens in here, I'm thinking a double bond between a carbon and an oxygen. That's just a good guess. 1.5, there are no half protons. What do I have to do to all these things? I need to multiply them. I'm trying to get to 8 total protons. If you're smart, you'll add this up and say 3, 4, right? 1.5 plus 1.5 plus 1 is 4, and multiply that to get to 8. Or if you're like me, and I'm not saying that's not smart, but if you're like me in Math Challenge, you'll go, well, let's just start from the bottom. Let's multiply everything by 2. So 1.5 times 2 is hard, but it's 3. 1.5 times 2, still difficult, but a little bit easier because it's familiar, is 3. And 1 times 2, I got that one in the bag, is 2. 6 plus 2 is 8. So we are good to go, right? Our 8 protons match our 8 protons over here. I don't do this to you that often, but it is fair game to show you a relative area that is not the exact number of protons. Watch out for that. I have been spoiling you all by showing you protons that don't need to be multiplied over here. So I'm going to now take those numbers and say 3 protons are here, 3 protons are here, 2 protons are here. Somebody tell me about this peak in blue. What has 2 neighbors? A CH3, smart student. A CH3 has 2 neighbors, right? So CH3 with a CH2 next door. And I don't know what else is beyond that. I wrote a CH3 here because there are 3 protons from this. And I gave it a CH2 because there are 3 peaks to that signal. Natalie, tell me about this signal in green. Natalie. It's a singlet, so what does that tell you? And how many protons are in that signal? 3. It's a CH3 with no neighbors. How do you get a CH3 to have no neighbors? You can do a couple different things. You can put an oxygen next to it, or since we think we might have a carbonyl in there, you could also use a carbonyl. I'd hold out for both of those, right? And actually, I saw a couple of correct answers or very similar, very close to correct answers on the Action Center. When you have esters, it can be challenging because one side of the ester has an oxygen, the other side of the ester has a carbonyl. Neither one of those atoms contain a proton, right? So if I need to isolate a group, I can do it on either side. Last thing over here, Ren, I don't want to permanently put you on the sideline. Tell me about this signal, Ren. No, you're back. Calling you back into the game. What's over here? That is not. That is 1, 2, 3, 4 peak. Quartet. So what kind of signal do I have? I have a CH2, and I need to give it 3 neighbors. Right? So that sure looks like this piece, sure looks like that piece. I don't know what's over here, but I'm going to go ahead and bet that this piece and that piece are related. This signal and that signal are talking about the same chunk of the molecule, just from one side versus the other. Right? Whenever, and you should, this is kind of standard, right? You'll see a CH3 with a triplet, and then a CH2 with a quartet. That means you have CH3 next to CH2. They are paired up like that. That's all I got. I got this chunk, that chunk, and this chunk. I've accounted for 1, 2, probably 1, 2, 3 total of my carbons, right? Because I'm thinking this piece and that piece are probably the same chunks related together. I need to account for 1 more carbon and 2 oxygens. So now I have to start trying to build this in somehow. From here, we are just guessing and trying to put our bigger puzzle pieces together. I need to link this piece to that piece to that piece. The only other piece of information I have here is look how far to the left that signal is. Pretty likely that that CH2 is next to what? An oxygen, something electronegative, something stealing from it. So instead of just having that be undefined, let's have a CH2 be next to an oxygen. That won't give it any neighbors over here, but it will draw that signal downfield and de-shield it. Now I need to get a CH3 in here somewhere. If I just tack a CH3 onto this side, I'm cutting myself short because now I don't have a carbon and an oxygen I should have. I also don't have my degree of unsaturation. Now, if I didn't do my degrees of unsaturation, I might want to try and go for this. And then Dr. Green's going to do something mean and be like, circling this up here a couple of times and be like, you didn't count your atoms, did you? And you'll be like, no, I didn't. I hate this. All right, so instead of just jumping to the CH3 there, how do I get my CH3 with another carbon and another oxygen? Make a carbonyl. And then put that CH3 on the other side of it. And I know it seems obvious because I'm drawing that same, draw boxes. I'm putting that same molecule underneath it here, but that's how you solve these things. Build up the pieces, get all your puzzle pieces in front of you, then start putting them together in a way that makes sense based on the NMR. That is the path to success here. Looking at an NMR, like a picture, and drawing a molecule does not work. Even if you're super good at an NMR, it does not work. It just, you lead yourself down paths that are really hard to come back from. We fall in love with our structure and then we're like, I'm going to make it work. I don't care if there's 11 bonds to carbon. It will work. Questions about that NMR? Solid. You know what? You guys should do one. You know how I like to just like pour stuff in beakers and leave it there unlabeled. Chloroform, things will set me on fire. I put a molecule in a beaker. I put the molecular formula on there, C4H7ClO2, there's chlorine in there. But I forgot what it was. So I took some instrumental analysis directions here, and I got an IR and I got an NMR. What is it? Enhance. Maybe. It's not that bad. What? Make it work. The green bar is, guys, there's no pleasing you. The green box is what's on the Zoom screen. So I'm trying to like hit the window. Now it looks all bad. This is not how I put it on. What's the problem? I can see it pretty well. Both of you is fine. Any order. Okay, 3 degrees. You might have a legit home back here. Did you really? What kind of marks on the far right? That's this is the spot. Because you really can't tell if you're there at all. From my eye, I'm just-
Yeah.
You add them. Let's just double check with the rest of the class here. Hey, class, when you have a halogen, what do you do with the hydrogen count? Add it. So that's right.
That makes sense.
Definitely. How'd it go? Yeah. Yeah, so the way you can tell that that is a doublet is that the line is thicker than. And it maintains its thickness, although it's. So if you really blow it up, get super close to this thing and it's not on the traffic projector, you can actually see it. At the top.
Yeah, good.
Bifurcate it a little bit.
And then a couple things. We don't know what kind it is.
Minus.
Yeah, well, if it was CO, I'd be like this thing. So I don't see that. Also, don't see, well, I guess
What you're doing is.
I don't know. It's an out. It could be an out. Is that long enough to be from Hill or is that not long enough?
Yeah.
Or saturated from the street.
Okay, drum shark feet, but it's not all the way to here.
So the OHP is really broad and it's absolutely not.
There's only three signals.
So it's just carbon.
There are only three signals. Yeah, that is a blow up.
Yeah, signal, but maybe it's S.
Okay, all right.
So that's all there's.
Wow.
Fine.
I don't know what's going on with there.
Yeah, well, like. Only if it doesn't matter.
But I mean, let's see, but here. I don't even know the answer to that. That is. Oh my gosh, you guys getting an MR? You like it a little bit, the whole time I've been saying you might like it a little bit, some of it are there. Oh,
That's good.
Yeah, it's definitely. Yeah, so it's not creation.
There, you'd be like, doing an MR. No, I get that.
Your reader, yeah.
You don't see us.
And then 3 neighbors. So one, oh, 2 neighbors.
Not yet, not yet.
So these might be are with you. Yeah, 3 like 2 years, so it's 2. And then this one.
Nice. They're so. Kirby, they just leave in the R. What?
No, it's just one. Well, it's single.
No, so it's double, single quartet. And then the peak on the far right for 3, the last 3 protons, peak on the left.
Yes. Well, it's got like 3 different, yeah. And then it's one.
To get to that one. And you're comparing that to C4H.
Oh, yeah, so it's like, they're in our. No,
This.
That one's gonna take care of it. Carbon, that's like. Nobody's not seen this.
Well, the fence was taxed, right, they taxed it. No. Use the tax very way. It's not what they're saying. But you're not doing that, especially when
That's.
Well,
Right, well, it's still has.
did it? Yeah. No, community farms doesn't realize burn and I was reading high school. That is what I'm.
Restaurants. Like that. That's like once a year.
It's like 5:30. I don't know if it's not, I just got like. I need to start. Yeah, that would be terrifying. Yeah. I just- But I think.
Look at that time. Have you guys heard of this thing called the flipped classroom?
Yeah.
So it's like this new trend in education where they're like, the thing that makes students really learn something is problem solving. So what we're gonna do is when we meet for class, we're only gonna problem solve, which sounds great, right? Like I love that. That's what I'm all about with Action Center. But then it leaves the point of, well, where do you actually learn the content? And that's the part that just pisses me off. Because the way you learn content in a flipped classroom, and I'm recording this. Yes. The way you get the content in a flipped classroom is you watch a bunch of videos. So you watch the videos and then you come in and just problem solve. I'm not down with that. But I do very much like walking around, working with you all, doing this sort of thing. If you like doing this too, guess what we do at Action Center every week? It's this. And the more people that come, the more fun it is. No, because OCHM 1 has like 8 people in it right now. Yeah, I need to zoom this out because I have no space to work. You guys are giving me such flack about this. So how many degrees of unsaturation does this here molecule have? 1. We add the halogen. Oh, don't do that. Go away. We add the halogen to the carbon. So this gives us a fake formula of C4H8. Our saturated formula is going to be C4H10. We're missing 2 hydrogens. That's 1 degree of unsaturation. What does the IR tell us? Basically nothing, and it has a carbonyl. Yay. So our 1 degree of unsaturation is absolutely that. We don't need to worry about putting a carbon-carbon double bond. We don't need to worry about putting a ring. There is a carbonyl in here. Given that there's another oxygen and there is no OH peak, very likely that that carbonyl is an ester, right? But it doesn't have to be. Some of you drew a molecule that was not an ester and it's perfectly acceptable. I have 2 oxygens in my formula. I have a carbonyl present. I do not have a carboxylic acid peak. So if I want to put that oxygen near my carbonyl, that's an ester without a proton. Okay, now what I'm going to do is take my protons over here and make sure the protons actually fit. So 3 + 3 + 1 is 7. So 3 protons over here, 3 protons over here, 1 proton over here. This is just a blow up of that last signal. You couldn't see it very well, but many of you probably heard me say this if I didn't tell you directly, that if you look at this line and compare it to the thickness of this line should look thicker to you. It just looks like it's in bold. The reason it looks like it's in bold is it's 2 lines that are pretty close together. Right? So they look like 1 line, but it's actually a doublet. So Will, tell me about this signal. It's a CH3 that's attached to a carbon with 1 neighbor. I don't know what else is over here, but it ain't carbon, it ain't protons. Somebody else, tell me about this one. CH3 with no neighbors, right? These are the ones that I think can be really cryptic, but once you start to see them, they can be really helpful because you know that it's to get it on the island, you need to start using the oxygen or the carbonyl to get it isolated from the rest of this molecule. And then somebody else over here, what do I got? A what with 3 neighbors? A CH. CH with 3 neighbors. Don't know what else I have, but that exists somewhere.
I guess like the part that I get hung up on is that there's 4 carbons and, because this is hydrogen that we're looking at.
That's right.
And so I'm like, that's where I get stuck. I'm like, where is the
Yeah.
other carbon going?
I think, did I talk about the allegory of the cave last semester with you guys? It stuck with a couple of you, and I know this is like a super out there nerdy reference. That's right. So Plato came up with this idea of life is like these dudes who were locked in a cave for their entire lives. And they were sitting against this cave wall and they were watching, a fire was behind them and they saw people walking past the fire and they saw the shadows projected on the wall. So for their entire lives, they were only looking at shadows and they understood all of the world around them was shadows. And one day they had like a prison riot and they busted out of the cave and they were like, what? There's more than just shadows? That's crazy because we've only understood life through shadows, right? They know pieces of it, but not the whole thing. That really overly complicated example is meant to say we are looking at the protons, looking at the shadows of this molecule, and we're assuming all these other atoms, all the carbons, all the chlorines, all the oxygens. We can't see any of that, but we see the shadows of things that are attached to them, and we figure it out from that. So it's kind of it works if you just really twist your mind around here a little bit. So a CH3 next to a carbon with a hydrogen, a CH3 next to a carbon with a hydrogen, those peaks are probably related to each other. CH3 by itself. Now you need to start building to try and get these things to separate out from each other. The answer to this, the true ground answer, is this. Oops, sorry, with chlorine. I saw several people put this in there. So that's my CH3 next to a CH. That's my CH3 by itself. The chlorine then is the other thing attached to this carbon. That's why it drags so far downfield. Many of you smarties came up with another structure that's totally valid, where you said, well, I can have a CH3 directly attached to a carbonyl. Oops, I can't even draw it. There. You came up with a structure that looks like this. If you drew that, you would get full credit as well. It sure is. That's a CH3. See, I just can't, I don't have the imagination. There we go. CH3. Okay. You're saying, well, a ketone would have a CH3 by itself. This would be a CH that's de-shielded next to a CH3. All of my splitting patterns match here. The only hang up with drawing a structure like this, and I'm going to put a box around it because I think it's clever and it fits. The only hang up is this proton is on a carbon that's in bad shape. This carbon has an oxygen and a chlorine attached to it. This molecule would be very unstable because of that. This carbon would not tolerate that very well. And this proton would get dragged really far downfield because of that. The fact that it's only about 4.5 tells us that, yeah, it's on a carbon with a chlorine, but it has another carbon attached to it. If it had a chlorine and an oxygen attached to it, we'd see that quartet like down here, pretty far de-shielded. But you don't know that. And so if you drew this top structure, full points. Very creative. Questions about NMR?
Now we know it.
That's right. Now that you know that this is not right, now it's wrong. Man, he just spent like 30 minutes talking about NMR again. I wonder if he's going to put a bunch of NMR on the lecture final. Yes, I am. Okay. Good talk. You guys done talking about carboxylic acid derivatives? Because I am. I want to tell you about some new chemistry we haven't talked about before in chapter 22. In chapter 22, I think can be a little frustrating, but it's also pretty cool because we're going to use a molecule we've seen before. We've talked about a bunch, but we're going to use it in a new way that we've not talked about. These are alpha substitution reactions. So we've actually kind of hinted at this before, but I can take this molecule, which is a ketone, but I'm going to refer to it as a keto. And I can turn this into an isomer where I take one of the protons from that carbon and I'm going to give it to the oxygen, and I'm going to move that carbon-oxygen double bond down. This is going to make something called a tautomer. What is the tautomer of the keto form? You knew it, Jayla. Yeah, just jump in there. You're like, I saw the enol. Blue, there it is. Jeez. Remember, these two things are called tautomers. We're going to do a lot of work, particularly with the enol and enol derivatives, because looky here, I've got an oxygen with lone pairs. Next door, I've got a carbon-carbon double bond. The lone pairs in this oxygen are electronically connected to that carbon. I am going to be able to, don't draw this just yet, but what we're going to do is move the lone pair from the oxygen down across that double bond and use that double bond to attack something else. There's a lot of chemistry that we can make carbon-carbon bonds or carbon bonds to other things at this position, which is on the carbonyl. What do we call that next to a carbonyl? Alpha. Carbon next to a carbonyl is alpha, next to that beta, gamma, delta, so on and so forth. It's not a hydride shift because we're actually moving a proton. So what Charles is wanting to know is, what's that mechanism, yo? He would probably say yo because he's cool. Wait, I don't need to write Mac again. So first we'll talk about this acid catalyzed. First step of all acidic catalysis. Protonate. What am I going to protonate? The oxygen. How did you guys know that? Because it's the same freaking thing every time, right? When you add a proton, if there's a carbonyl, give the oxygen a proton. That is going to make this activated carbonyl. Here's the annoying part. We're going to be pulling protons off of carbons that normally have multiple protons. If you draw one proton, draw all the protons, right? I don't want to see any of this. Yeah, you only need that proton, but there are two others there. So if you want to just write CH2, that's fine. Make sure if you label one, you need to label all of them. Water is going to come in and act as our base. How do I show that? Form an enol. Yeah, so I've let it slip for long enough. We're going to start using big boy and big girl languages. Language? It's been a long day. It's been a long 2023. That is not a hydrogen. Why? It's a proton. A hydrogen is a proton and an electron. When a hydrogen makes a bond to something, its only electron is now tied up. It no longer belongs to that. So this is literally just a proton floating out in space. So remember, we talked about these, doesn't take a hydrogen. That's OChem 1 stuff. It's going to take a proton. When I do that, what's it going to do next? We're going to take that bond and move that bond over here. And then we're going to push this up onto the oxygen, right? So this is the thing that's pulling on electron density. That oxygen with a positive charge is kind of why that proton becomes acidic. That makes an alkene alcohol. Or our enol. Cool. Not carboxylic acid, cool, but cool. It can be done in acid. Can it be done in base? Yes, it can. Is it shorter? No, it's not for once in its life. This is a two-step mechanism as well. The basic catalysis. What's the first step of every basic catalysis? Yeah. Sorry, Susan. Need to attack a carbonyl or take a proton, right? So I don't ultimately want to add any more oxygen to this. So if I have base in here, I like that you guys are saying the first step is for the O- to attack the carbonyl. It could, but that's not going to lead to any productive pathway because then I have to break a carbon-carbon bond. No leaving group here, no leaving group there. So instead, just like I showed you with this, where a base took a proton from the alpha carbon, a base is going to take a proton from the alpha carbon straight away. This isn't going to make an enol, it's going to make something even more important. This is called an enolate. It's an enol anion. Make a note, it's special. We'll come back to that later, but we're going to use enolates a bunch in this chapter and the next chapter. If I want to turn an enolate into an enol, what do? I need to grab a proton. Let's use just water, right? Since I didn't give you an acid catalyst. Because if I use water, and that takes a proton, I know it feels uncomfortable, but it'll make hydroxide, which means I regenerate the thing I started with, so that's great. That forms an enol. Every time we make one of these enols or enolates, that is a alpha carbon that has potentially a lot of electron density around it, because all of these have an O- or an oxygen with lone pairs that can push down and push over from the alpha carbon. So the alpha carbon is where the magic's going to happen in all these reactions, for sure.
So the alpha carbon, they just go with the one that's closest to the other carbon.
Any carbon directly attached to a carbonyl is an alpha carbon. Any alpha carbon that has a proton is a place where you can create a nucleophile. So before we were just like, oh, ketones, they do these things. Now ketones and aldehydes are going to do a bunch of different things. So there is no alpha carbon between an acid anhydride, but there could be on the ends. So like the oxygen in the middle of an acid anhydride is not an alpha. It's technically an alpha oxygen, but a different thing. We use alpha, beta, gamma, delta to describe the carbons, not other atoms. And in here. Correct. So this is acetic anhydride. The alpha carbons, that's an alpha. The alpha carbons are there and there. Cool. Have a wonderful weekend. I will see you all on Monday.
Okay,